Machine learning has become synonymous with innovation, but for most of us, it's also synonymous with frustration. Training ML models on everyday machines often leads to slowdowns, crashes, and unfulfilled ideas. Why? Because the tools we rely on, like Python, are powerful, but they were never optimized for constrained systems. Python's flexibility comes at a cost: inefficiency. Single-threaded execution, lack of true parallelism due to the global interpreter lock, and inefficient memory management make it unsuitable for resource-constrained environments. But what if there was a solution? A way to make machine learning efficient, even on the machines most of us use. BarX is built on Python, accelerated by Cython, and powered by C++. BarX utilizes mathematical optimizations like Strasson's algorithm for matrix multiplication. Instead of the traditional O(n)(3) complexity, Strasson's approach reduces this to O(n)(2.81) by splitting matrices into submatrices and performing 7 recursive multiplications instead of 8. BarX also uses reduced precision arithmetic. By using 16-bit floats, FP16, instead of 32-bit floats, FP32, we can halve memory usage and double computation speed with a marginal loss in accuracy. Gradient accumulation is another key optimization. Instead of computing gradients for the entire batch, we compute them for smaller batches and accumulate them before updating weights. This allows us to use larger effective batch sizes with limited memory. BarX also employs algorithmic efficiencies, such as using sparse matrices. This means that for matrices with a lot of zeros, we only store the non-zero elements and their indices. This reduces complexity from O(n)² to OK, where k is the number of non-zero elements. Hash maps are used instead of lists for faster lookups. Searching a list has a complexity of O(n), while searching a hash map has a complexity of O(1). BarX uses operating system-level optimizations like task scheduling. This involves using multi-threading to assign machine learning tasks across all available CPU cores. BarX employs SIMD optimization, which means performing operations on multiple data points simultaneously. This can significantly speed up computations. Memory mapping is used to map large datasets directly from disk to memory. This means data is streamed in chunks, seamlessly feeding into the CPU without needing to load the entire dataset into RAM. Let's see BarX in action. We'll train a small CNN on a machine with an i3 processor and 8GB RAM using a 1GB image dataset. BarX dynamically adjusts batch size, uses custom C++ kernels, and streams data via memory mapping. Resource graphs show memory and CPU usage stabilizing as BarX adapts. This is BarX, the most efficient and powerful programming language built on Python. By combining mathematical brilliance, algorithmic efficiency, and system-level optimizations, BarX is not just ready for the challenges of today, but also for the possibilities of tomorrow. BarX, Tensor-Ready, future-ready.